In this lesson, we're going to go over antiderivatives. So this is really starting the second branch of calculus, which is involving integrals. So antiderivatives can kind of help us do a couple of different things. So here are some real-life scenarios which use antiderivatives. So you can kind of read them yourself. But basically, if you know the derivative or a rate of something and you want to know the amount, we can work backwards now from the derivative to find the antiderivative, which will help us find these numbers that we're looking for. So these are called antiderivatives. So what exactly is an antiderivative? It's the backward operation which goes from the derivative of a function to the original function itself, in addition with a constant. So a function f is called an antiderivative of little f on an interval if big F prime of x is equal to little f of x. So basically there's two different notations that you might see, and I have them written out for you here. So sometimes we use a capital F to mean the antiderivative or the original function, and then a little f to indicate the derivative. We're used to seeing this one on the right, where the little f is the antiderivative or the original function, and then little f prime is the derivative. Okay, so we're used to seeing the one on the right, but we also can see the one on the left. So just because you see a little f doesn't mean it's the original. It could be the derivative, and we're trying to find big F. So just be aware of both notations. Okay, so we're going to kind of look back a little bit at derivatives. So here we have big F of x. So this is our original function, and they want us to find the derivative. So we know how to do that. The derivative of big F of x, we're going to call it little f of x based off of our notation from the previous slide. When I take the derivative of 1/3 x cubed, I'm just using the power rule. So this is going to give me x squared. Now we want to find the derivative of f of x equals 1/3 x cubed plus 100. So again, the derivative, I'm going to use the power rule. So the derivative of 1/3 x cubed is x squared, and the derivative of 100 is 0. So what we can notice here is that both of these give us the same derivative, but with different functions. So we started with the original function that are two different original functions. The second one has a plus 100, the first one does not, but their derivatives are the same. And this is really important. So we're going to go to here. So if f is an antiderivative of little f on the interval, then the most general antiderivative is big F of x plus c. So that plus c is super, super, super important. So it's really important that when we take antiderivatives, we include this plus c, which is an arbitrary constant. So later on, we'll be able to solve for c. So we actually have a number there instead of that c that's going to represent our constant. But if we look at these different graphs here, all of these graphs have the same derivative. If I took the derivative of all of these functions, all of them give me a derivative of x squared, which is what we saw in the previous slide. But all of these functions are different, right? These are families of functions. So it's the same exact function, but they're translated either up 3, up 2, up 1, not at all, down 1, down 2. So even though they look different and they're in different spots, they're different functions, they have the same basic shape, so they do have the same derivative. Okay, so it's really important to include that plus c because there could be some other number that's added to it. So let's find the most general antiderivatives of each of the following functions. Now, when you're finding antiderivatives, it takes not a little bit of practice, but you just have to kind of think a little bit backwards. So if we have f of x equals sine of x, these are our derivatives. So we're trying to find the general antiderivative. So we want to think of, if I take the derivative of the original, what is going to give me this value? So the derivative of what is going to give me sine x? So the original, the antiderivative, f of x, is going to give me negative cosine of x plus c, right? We can always double check by taking the derivative of the antiderivative. So if I take the derivative of this, the derivative of negative cosine of x is going to be positive sine of x, because the derivative of negative cosine, or the derivative of cosine, is going to be negative sine. So we have a negative negative sign, which gives us positive sine. Okay, so these are things that you can just remember. It's one of those memorization things, but you can also just kind of work backwards. So if you can think about what can I take the derivative of to get that, you can think of it that way as well. So let's look at the second one. So the derivative is 1 over x. So when I take the derivative of what, do I get 1 over x? So this would be the ln of the absolute value of x plus c. So we put the absolute value because whatever, the ln of any positive number works, but the ln of a negative number won't exist. So we always say the absolute value to make it always positive. So if we were working backwards, the derivative of the ln is 1 over x, assuming that there's x in the inside. Okay, and then e to the x, our antiderivative would just be e to the x plus c, because the derivative of e to the x is e to the x. Okay, so now we're going to look at what happens with the power rule. So to find the antiderivative of a power function, we have to reverse the power rule. So what we're going to do is look at the power rule normally, and then we're going to look at how we reverse it. So let's consider our function to be y equals 5x to the fourth. All right, so here is our original function. So we're just remembering that the power rule says to bring the power in front, where it will multiply to the rest of the derivative. So if I have 5x to the fourth, right, I'm bringing the 4 down to multiply to the 5. And then I'm reducing the power by 1. So I have 20x to the fourth, but then I'm reducing that 4 down to a 3. So it becomes 20x to the third. Okay, so it's just a longer, convoluted way to get to the derivative that we already know. When we look at this, we should know by now that y prime, I'm just going to write this here, is equal to 20x to the third, right? Because we multiplied the 4 times the 5, and then we subtract 1. So that's what we're doing. But now, if we want to reverse the process in order to find the antiderivative of things, what we need to do is reverse the order of the steps and reverse the math in each step. So I'm going to start with the derivative. The derivative of that previous problem is 20x to the third. So I know what the antiderivative should be because of the previous slide. So everything we do, we're going to just reverse. So instead of reducing the power by 1, which was our last step in finding the derivative, we're going to make that our first step, and we're going to reverse it by adding 1. So I have 20x to the third. I'm really going to add 1 to the exponent, so I have 20x to the fourth. And then the first rule for finding the derivative was to bring the exponent down in the front and multiply. So our second thing that we're going to do when we're reversing it is we're going to take the exponent that's in front and bring it down, but we're going to divide it instead of multiplying it. So we really have 20 over 4 x to the fourth, which gives us that 5x to the fourth. And that's our original function. So we're increasing the exponent by 1, and then we're dividing the number in front by the new exponent. So it seems like a little bit confusing. So let's look at it in the most generic sense here. So what I'm doing is I'm taking my exponent of n, and I'm going to add 1 to it. And then I'm going to divide whatever's in front. So right now there's a 1 in front. I'm dividing it by the new exponent, n plus 1. All right, so we can also just say that this is x to the n plus 1 over n plus 1. Okay, so add 1 to the exponent, divide whatever's in front by the new exponent. So here's a table of general antiderivatives. So I would pause the video right now and I would write these down. These are very good to have handy, and these are ones that you should memorize. They're very important ones to have. I'm not going to talk about them right now, but we're going to reference this later when we do some problems. So just remember that if you're ever stuck, think about what the antiderivative is. If you take the derivative of the antiderivative, you're going to get the function. Okay, so all of these antiderivatives, if you take the derivative, you're going to get the function. So let's do some problems. So find the most general antiderivative of the function. So here we have all powers, which are great. So we're going to take the antiderivative. So I'm just going to show all of the little steps first. So I have the 6x I'm going to increase the 5 by 1 to make it 6, and then I'm going to divide by 6. And then for the next one, I have negative 8x. The 4 is going to increase by 1 to become 5, and then I'm going to divide by the new exponent, which is 5. And then I have negative 9x. I'm going to increase the exponent by 1, so that becomes 3. And then I'm going to divide by the new exponent of 3. And then I always have to put plus c. So I tack on that plus c. Do not forget to put the plus c. So now I'm just going to simplify this a little bit. So the antiderivative is going to be x to the 6, because the 6 will cancel, minus 8/5 x to the 5th, minus 9 divided by 3 is 3, so 3x to the 3rd, and then plus c. And again, you can double check your work by taking the derivative. So if I take the derivative, I'm just going to show this really fast here. Right, if I take the derivative, f of x, I'm going to have 6x to the 5th minus, I'm going to multiply 8/5 times 5, so that's going to give me 8x, subtract 1, 4. And then here I have minus 9x squared. And then since c is a constant, the derivative of a constant is just 0. So this is where I end up with my derivative, which is exactly where I started. Okay, so let's look at this one. So it's going to be helpful when you have radicals to change them to rational exponents first. So I'm going to take the same exact derivative here, and I'm just going to rewrite it so there's rational exponents. So this will become 3x to the 1/2, and this will be minus 2x to the 1/3. So now that I have it written like that with exponents, it's going to be a lot easier to take the antiderivative. So I have the antiderivative, original function f. So I'm going to increase the 1/2, so I'll just write this again like this. Increase 1/2 by 1, so I'm adding 2 halves, so that's going to be 3 halves. And then I'm going to divide by 3 halves. And then I have minus 2x. I'm going to add 1 to the 1/3, so I'm adding 3/3, so I get 4/3. And then I'm going to divide by 4/3, and then I have plus c. So the more you do this, you're not going to have to write out every step. I'm just kind of showing you that right now so we can get comfortable with this. So 3 divided by 3 halves is going to give me 2. So I have 2x to the 3 halves. And then 2 divided by 4/3 is going to be 3 halves. And this is x to the 4/3. And then plus c. So you could change these back to radicals if you wanted to, but you don't really need to. So we're just going to leave it like that. That's our general antiderivative. All right, so let's look at this one now. Now, if you have something where you can use kind of algebra to kind of simplify a little bit or kind of break it up a different way, you want to do that because when we're finding the antiderivative, the product rule and the quotient rule don't really have an inverse. So we're going to get into later how you do more complicated things. But for right now, we don't want to try to find some type of like reverse product rule or reverse quotient rule. So we're going to try to simplify things as best we can. So the first thing I'm going to do is rewrite this. So I have f of x equals 4 sine of x. So if I break this up, I'm going to make this, I'll show this in a couple steps, 2x to the 5th over x minus the square root of x over x. Right, so I'm breaking it up and I'm dividing each thing by x. So when I do that, I'm going to simplify the exponents. So 5 minus 1, this is going to give me 2x to the 4th. And then this is really x to the 1/2. So when I do 1/2 minus 1, this is going to give me negative 1/2. So now that I have everything with exponents, it's a lot easier now to take the antiderivative. So the antiderivative is going to be, so the 4, because there's a constant in front, you can keep that constant of 4. The antiderivative of sine of x is going to be negative cosine x. So you could refer back to that table of antiderivatives or just think about the derivative of this will give us that. So now I take the antiderivative of this. So I'm going to increase 4 by 1 to get 5 and then divide it by 2. So 2/5 x to the 5th. And then I'm going to increase the negative 1/2 by 1. So that's going to be 1/2. So I'm going to divide this negative 1 by 1/2. So that's going to be negative 2 x to the 1/2, and then plus c. And here's my general antiderivative. Okay, similarly on this one, we have something where we might think we have to use a reverse quotient rule, but that's not a thing that we're going to use. So let's see if we can break this up. So we're going to make this f of x equals, I'm going to divide each thing by x to the third. So x squared over x to the third is going to be x to the negative 1. 2x over x cubed, that's going to be 2x to the negative 2. And then this is going to give us negative 3x to the negative 3. So now we're going to take the antiderivative. So it's really important here to make sure that you pay attention to, I'm going to actually go back to this really fast. If we notice this right here, oops, when we have a power function like x to the n, we do the thing that we talked about by increasing the exponent by 1 and dividing by that. However, you can't do that when n is equal to negative 1. When n is equal to negative 1, if we increase it by 1, we get 0 as the power. So whenever that happens, this is really going to be using this one, right? Because if I have x to the negative 1, that is the same thing as saying 1 over x. So when I have 1 over x, the antiderivative is the ln. So we always want to make sure that we pay attention to that. So x to the negative 1, that's just the ln, that's just 1 over x. So my antiderivative will be ln of the absolute value of x for that piece. And then the rest I can use the kind of reverse power rule here. So we're going to increase by 1 to get negative 1 and then divide it. So we're going to get negative 2x to the negative 1. And same thing here. Increase negative 3 by 1, so we get negative 2, and then divide it. So it's going to be positive 3/2 x to the negative 2, and then we have plus c. So we can leave it like that. We could rewrite it with the exponents in the denominators so that they're positive, either one. Okay, and we'll look at another one real quick. So here we've got 2 sine of theta minus secant squared of theta. So again, I would use your antiderivative chart that I showed you before if you're not sure. So the 2 is the constant. I can keep that. Derivative, antiderivative of sine is going to be negative cosine of theta. And then the antiderivative of secant squared is going to be negative tan of theta, right? Because the derivative of tan theta is secant squared. And then plus c. Okay, so an equation that involves derivatives of a function is called a differential equation, and the general solution includes that arbitrary constant, that plus c. But if we're given extra conditions or information, we are able to solve for c so we can get a specific solution. So whenever we don't have additional information, we must include that plus c. When they give us extra information, we're going to solve for c and actually have a specific solution. So let's look at this problem here. So find f if f prime of x equals this thing and f of 0 is equal to negative 2. So they're giving us a condition. So I know that I'm going to be able to solve for c. So first thing I have to do is I have to find the antiderivative. So the antiderivative of e to the x will be e to the x. And then the antiderivative of this, if we remember, 1 plus x squared to the negative 1, that's really just 1 over 1 plus x squared. And if you look at the chart for antiderivatives, this is the antiderivative for the inverse tangent. So the derivative of inverse tangent is this 1 over 1 plus x squared. So this is really going to end up being 20 inverse tan of x. And then we're going to keep that plus c because this is our general antiderivative. But now we know a specific piece of information. We know that f of 0 equals negative 2. So we're going to plug that in. So f of 0 is equal to e to the 0 plus 20 inverse tan of 0 plus c. And we know that that's equal to negative 2. So e to the 0, that's 1, plus 20. Inverse tan of 0, that's 0, plus c equals negative 2. So we're just going to end up with 1 plus c equals negative 2, in which case c is going to equal negative 3. So since we know what c is, our final answer is going to be writing our antiderivative, but instead of the plus c, we're going to actually put in the negative 3. So our f is going to be e to the x plus 20 inverse tan of x. And remember, you can use arctan instead of the inverse tan if you prefer. And then we have minus 3. Okay, so now we have kind of not a little bit harder of a problem, but there's kind of two different conditions that they're going to give us. So find f, right, our original function, if f double prime of x equals this. So they're giving us the second derivative, and we need to find the original. So what we're going to have to do is find the antiderivative twice, right? So if we think about, like, just going to write this over here, like the circle of life that we had like the x of t and the v of t and the a of t. This is the same idea, right? The second derivative is similar to the acceleration. So I have to go twice that way or twice this way. So if I'm starting with the second derivative, which is similar to the similar to the acceleration, and I want to find the original, in this case, like the position, I need to go backwards twice. So I have to take the antiderivative 2 times. So first, we're going to start with finding the first derivative. So I'm going to go back 1 time. So f prime of x, let's take the antiderivative. So we're going to increase the 2 to 3 and then divide it. So 4x to the third. The 6x is an exponent of 1, increase it by 1 and then divide it. So that's going to be 3x squared. And then 4, it's really like x to the 0. So we're going to increase it by 1 and then divide it. So that becomes negative 4x. And then we have plus c. So we don't have any information about f prime. The two conditions they gave us were about f. So I can't plug anything in right now and solve for c. So what I'm going to do is go find the antiderivative again so I can find actual f here. So f of x equals, again, increase by 1 and divide it. So this is going to give me x to the fourth, increase by 1 and divide it. So I have x to the third, increase by 1 and then divide it. So I have negative 2x squared. And then this is like cx to the 0. So increase by 1 and divide it. So this is going to give me cx. And then I have another constant because I always have to add an arbitrary constant. But I already use c as a constant, so I'm going to call this one d. So now I have the conditions I can use. Now, you might want to pick one versus the other. However, there is one that we should use. So if I try to use 1, let's say, if I plug in 1 for all the x's, I'm going to end up with a c and a d, which is not going to help me solve for anything. But if I plug in 0, it's going to get rid of this because c times 0 would be 0. So I'm going to use f of 0 first. So I'm going to do f of 0. I'm going to plug in 0 for all my x's. So 0 to the fourth is 0. 0 cubed is 0. 2 times 0 squared is 0. C times 0 is 0. And then plus d equals 4. So this tells me that d is equal to 4. So what I can do now is go back up to my function and get rid of the d and put in 4. So now I'm going to find f, I'm going to use the information for f of 1. So f of 1, and I'm going to plug 1 into here, and I'm going to use 4 in place of d. So 1 to the fourth is 1, 1 to the third is 1, 2 times 1 squared is 2, c times 1 is c, and then I know d is 4, and then this whole thing has to equal 1. So when I solve this, 1 plus 1 is 2, minus 2 is 0, so c plus 4 is equal to 1, so that means c has to equal negative 3. So now, to find my antiderivative, I'm going to plug in my c and my d, so I have x to the fourth minus x to the third minus 2x squared, and then c is now negative 3, so this is going to be negative 3x, and d is 4, so plus 4. And there's my antiderivative. Okay, so we're just going to look at another one, but this in terms of like position. So find the position function s of t if the acceleration is equal to this, and then they tell us something about s and v. So s of 0 is equal to 0, and v for the velocity of 0 is equal to 4. So first thing I have to do is find the velocity. So v of t, I'm going to take the antiderivative of the acceleration. So the constant of 3 can stay. Antiderivative of cosine of t is going to be sine of t. And then I'm going to say this minus 2 can stay. And then the antiderivative of sine of t is negative cosine of t. So this is going to become positive because it's minus a negative cosine of t. And then I have that arbitrary constant, so plus c. But they told us that v of 0 is 4. So we're going to use that information. So v of 0, so that's going to give me 3 times sine of 0 plus 2 times cosine of 0 plus c equals 4. So we get sine of 0 is 0 times 3, so 0. Cosine of 0 is 1 times 2, so we get 2 plus c equals 4. So when we solve this, we get c is equal to 2. So my velocity function, I'm going to go back to v of t. Now I'm going to plug in what c is. So my velocity is 3 sine of t plus 2 cosine t plus 2. So that is my velocity function. But I want to find the position. So now I have to find the antiderivative of the velocity to find the position. So the antiderivative of 3 sine t is going to be negative 3 cosine t. The derivative of 2 cosine t is going to be 2 sine t. The derivative of 2 is going to be 2t. And then I'm going to use plus d because we already used c, and that's already equal to something else. So now we know s of 0 is 0. So I'm going to s of 0, plug that in. So I have negative 3 cosine of 0 plus 2 sine of 0 plus 2 times 0 plus d equals 0. So then I get here negative 3 plus 0 plus 0 plus d equals 0. So I end up with d is equal to 3. So we can then just plug that back in to find our position function. So negative 3 cosine of t plus 2 sine t plus 2t, and now d is 3, so plus 3. And then here, is our position function. Okay, and then we'll just do one more for good measure. Particle, it moves in a straight line and has acceleration given by a of t is that. Its initial velocity is that, and its initial displacement is that. Find its position function. So same idea as before, I'm just going to kind of go a little quicker through this one. So our velocity, take the antiderivative of 6t plus 4. So this is going to give me 3t squared plus 4t plus our constant of c. They're telling us that v of 0 is negative 6. So v of 0 is going to give us, I'll do 3 times 0, but I'll just jump to the step of that's going to be 0 plus c equals negative 6. So c equals negative 6. So our velocity is going to be 3t squared plus 4t minus 6. So now we have to find the position. So s of t, we'll take the antiderivative. So that's going to give us t cubed plus 2t squared minus 6t plus d. We're going to use our initial condition that s of 0 is equal to 9. So s of 0, if I plug in 0 for t, this is going to give me 0 plus 0 minus 0 plus d equals 9. So d is equal to 9. So then our s of t function is going to be t cubed plus 2t squared minus 6t plus 9. And there is our position function.